Okay, video 21C. This should be it for me, and then you'll have one more with Joe. 21D is the last video in this course. So, we are looking at a two-sample confidence interval for the difference in means. Joe just got done doing the hypothesis test for this one. Now we're going to support his results with a confidence interval. So we can support our hypothesis test by calculating confidence intervals for a range of plausible values for the difference in means. So in that CCLA test example, we rejected the null hypothesis and concluded that grads do better on average than first-year students. So the next logical question might be, well, by how much do they do better? So our best guess, we could look at what happened in our sample, and we could look at the average for the grads and see how that differs from the average for the first-year students. And that might be a starting place for our best guess. So you might recall that for the grads, the average was 1,101, whereas for the first-year students it was 1,026. And that difference, we already even pointed out, was a 75-point difference. That might be our best guess. We can take that number, add and subtract a little bit to that to get an interval, but we'll use this as our starting point for that interval. All right, let's look at the formula then that we'll use to look at a two-sample T interval. So we've looked at confidence intervals for one-sample problems. Now we're going to look at a confidence interval for the difference of two means. Remember, we're doing this for the difference of two population means, but we're using sample data for this. So, like all confidence intervals, we'll take our best guess, plus and minus some margin of error. And in this case, when looking at the difference between two means, our best guess is the difference between those two sample means. For the margin of error, since this is a mean problem, the margin of error will have a critical t-score. And then we need to multiply by something that involves those standard deviations from our two samples. So we'll take the standard deviation for the first sample, square that, divide by the sample size for the first sample, and do the same thing with our second sample. This critical t-value will have degrees of freedom that, again, we'll provide for you. The formula for them is a bit complex. We may discuss it more in class here, but I'll make a note that for now, we're going to give these to you. There is a formula, but we're going to provide that for you. Okay, so we're going to construct a couple of these in a second. So formula is getting a little bit more cumbersome, but the idea is exactly the same as it was when we had a single sample with a mean. Note number one. Oh, just wrote this down. But in this notebook, we're going to give you the degrees of freedom because the formula is complicated. When using StatCrunch directly, the degrees of freedom will be calculated for you. So a note on the degrees of freedom. Second note, when calculating a confidence interval for the difference of two means, or two proportions for that matter, we're going to be curious to see if 0 is inside that interval. If 0 is not in the interval, then we will have statistical evidence that there is a difference in the population means or proportions, depending on the problem. Whereas if 0 is inside the interval, then we don't have any evidence of a difference in the population means. It could be plausible that those two values are the same. So 0 is going to be a pretty critical value that we're looking for, whether it's a mean problem or a proportion problem. We'll be curious to see if the interval contains 0. So we're going to look at ours when we're finished to see if it contains 0. All right, now let's do a couple of examples. Continuing with the example that Joe did in the last video on the CCLA results. We concluded that graduates do better on the CCLA test, but by how much? So give a range of plausible values with a 95% confidence interval for the true difference. Degrees of freedom are given as 124.699. Okay, so we have two sets of information that are independent samples. We're asked to construct a confidence interval for the true difference. We're getting a confidence interval for the difference of two means here. And you'll recall from the last example, we'll stick the same way. We called the grads, the existing students, the first group, and the first year students, the second group. So we're going to stick with that same ordering here. So we're ready to construct our confidence interval. I think I have a clean slide to show my work. Yep. And so using that formula that we just had up here, to save room, I'm not going to rewrite it down, but we looked at the difference of the two sample means, so we'll do that first. The first sample the grads had a sample that was 1,101. The first year students had a sample mean of 1,026. So this is our best guess. We already know that's 75. Plus or minus, we'll have a critical t-score here. This critical t-score you're going to get from StatCrunch. From StatCrunch. Use that T calculator. Degrees of freedom is given, 124.699. And we want this for a 95% confidence interval. Keep in mind what your picture ought to look like here. You're finding this. So you ought to verify, pause this, make sure you can get this, that critical t-score is 1.979 from StatCrunch. And then we'll have the square root piece that contains the standard deviations and our sample sizes. So from our first sample, we'll take 133 was the standard deviation squared. The first sample, our graduates, we sampled 66 students. And then in the second sample, the sample standard deviation was 158. We square that, and there were 65 students in that sample. So we already know that this difference here between our two sample means was 75. And then if you compute the margin of error over here, we're going to take 75, give or take what? This ends up being 50.54. And so finally, I'll take my sample mean minus the margin of error, the difference of the sample means plus the margin of error. And we'll end up with our confidence interval. This will range from 24.46 to 125.54. Don't forget what this is. This is a confidence interval for the difference of two means. Right? And so if we interpret this confidence interval, and keep in mind the order that you subtracted, we looked at grads minus first year. Does that interval contain 0? It does not, right? This entire interval is positive, which would indicate here that grads perform better than first year students. This difference is always going to be positive. How much better do graduates perform than first year students? On average, they performed somewhere in the range of 24 to 125 points better. And we can say that with, I believe this was 95% confidence. So we are 95% confident that grads do better, let's say on average, 24.46 to 125.56 points better. We could put the on average here. than first-year students. On the CCLA. So, we had concluded from that hypothesis test that grads did better. How much better are they performing? We're 95% confident that on average they're performing 24.46 to 125.54 points better on average than those first-year students. So this gives us that range of values. So clearly this agrees with the results of that hypothesis test. If for some strange reason we made an error and we got a confidence interval that went from, say, negative 24 to 125, we'd say, wait a second, that interval contains 0. That kind of suggests that there wasn't a difference. That didn't agree with our hypothesis test. We better go back. We must have done something wrong. Your results of your confidence interval should support what you found in your hypothesis test, which we do here. All right, so that's the first example in this lesson. Let's get to the second one. So next example. All right, a while ago, for statistics, we switched textbooks. This was before we sort of moved to this book that Joe has authored for us here. So the old book, when we taught statistics, was believed to be easier on the homework when compared with the new book. Again, not regarding what we're doing now, but a while ago. So there was an older book believed to be easier on the homework compared to the new book. Professor Koop downloaded all the homework scores for the spring 2011 and compared them to all of the homework scores from spring 2010. And we're going to treat these 2 semesters as representative samples of students taking the course from the old book versus the new book. The scores of 0 were deleted from both data sets. These were students that maybe dropped out or stopped attending. So we did exclude all those from both sets of data. And we have summary stats. And so here they are. You have these in your book. For the new book, we looked at 1,123 scores where the average was 87.512, whereas in the old book we looked at 458 student scores and the average was 90.82. And you see standard deviations and other values given there as well. Run the appropriate hypothesis test to determine if we have evidence that the new book has a lower online homework score, indicating that it is indeed harder than the old book. Show all the steps. The degrees of freedom have been provided for us. We will use 920.48. Okay. We're going to call the new book sort of sample 1 and the old book sample 2. Joe talked in the previous video that a lot of times he likes to take that difference to make it positive, which is fine. We could totally make the difference with this one positive. This is an example where the difference is going to be negative. We're going to test for a negative difference. I'll write that up in a second. For a lot of these, you could run the hypothesis test either way. Same thing with the confidence interval, and you ought to get results that tell you the exact same thing. So I'll try to make a couple of comments with that along the way with this one. Okay, so here's what you have. We're to go ahead and run the hypothesis test. And then when we're finished with the hypothesis test, we'll back up the results of that with a confidence interval. So for our hypothesis test, let's first, for one thing, make sure we're doing the right kind of problem. We want to run a hypothesis test. We want to see if the new book has a lower online homework score than that old book. We have, ask yourself, is this a mean problem or a proportion problem? We've got homework scores, right? That variable is quantitative. When you're dealing with quantitative variables, it's a mean problem, so it's a mean problem. Ask yourself if you have 1 or 2 samples. Clearly we have 2 samples worth of data. And are those 2 samples independent or dependent? Are they paired or do they sort of have nothing to do with one another? These are from 2 completely different semesters, right? The students aren't grouped in any way. So we have 2 independent samples. For conditions, Yeah, I'll put those here. We commented that our variables are quantitative. I think it's fair to assume that our samples are at least unbiased. Our sample sizes are rather large. They're well above 30. So even though we don't have the raw data, we couldn't see what a histogram looked like, our sample sizes are well above 30. The last condition are our sample sizes less than 10% of the population. You know, if you think about every student that's ever had statistics ever, certainly there's a lot more. This is definitely less than 10% of all students that have taken statistics ever out of those two books there. So I would think that that 10% condition is also okay. All right, so now I've gotten the conditions out of the way. Let's set up our hypotheses. So now I'm going to go to my clean slide. Run the test. All right, we're looking to see, does the new book have lower online homework scores than the old book? If the homework if there's no difference in the difficulty, we'd expect the averages to be the same. It says, does the new book have lower online homework scores than the old book? So because it says that, I'm going to test this. There is absolutely no reason why I could have changed my mind and said, you know what, I'm going to see, are the averages on the old book, are they higher than the averages on the new book? And I could have made this into an upper tail test again. I would end up with the same results. We do want to show you an example of the lower tail test, so we're going to leave that as less than. Okay, let's get to our test statistic. T. You have the formula. I'm going to just go ahead and fill it in. We're going to look at the difference in the two sample means. I'm going to look at the sample mean from the new book. You have that in the table above. The average out of the new book was an 87.512. The average score in the sample from the old book was 90.82. And then we'll divide by this square root that contains our standard deviations and sample size. So again, for the new book, standard deviation was 19.503. That gets squared. And in that new book, we looked at a sample of 1,123 students. And then from the old book, our standard deviation was 17.868. Again, that gets squared. And from the old book, we had a sample of 458 students' homework scores. Make sure you can type that in your calculator. Take this entire difference divided by the square root, and we ought to get a test statistic value of negative 3.25. So we kind of already have an idea of what we're going to do based just on the test statistic. This difference in homework scores is 3.25 standard errors away from zero, below zero. So let's use that test statistic to get the p-value. Always draw a picture for that p-value. Here's t, centered at 0. Our test statistic is down here, pretty far down. And since our alternative had been less than, we're going to shade the area below, and that area is the p-value. Use the StatCrunch calculator. Recall that the degrees of freedom for this t-curve was given in your course notebook as 920.48. So use that t-calculator. You should get a p-value. We're expecting something fairly small there of 0.0 .006. So very small p-value. I don't think we're given a significance level in this one, but if we were, that would be smaller than any practical significance value you'd be given. So because this is so small, we will definitely reject the null hypothesis. And then again, once you make your decision, reject, fail to reject, make sure you write a conclusion in the context of the problem. What does that mean? If we're rejecting the null hypothesis, we did find evidence that the new homework here appears to have lower scores than the old homework, that the new book appears to be harder, if you will. But the average scores on the new textbook homework tend to be lower than the old. So we do have statistical evidence, pretty strong statistical evidence, that the new book has harder homework, if you will. We might say your scores on average are lower. If you run this test and you had wanted to flip this around, you'd get the same thing. If we tested, is the average for the old book, are those scores greater than the average for the new book? The only thing you have to keep in mind is whatever order you have up here, whatever order you've written them in, that's the order you have to subtract in your test statistic. We're looking at new here and old here. If you flipped these around, we would have had to have subtracted in a different order. These things would flop too, but that would make a difference on the bottom. The only thing that would change this test statistic would become positive. But it'd be an upper-tailed test, so the p-value would remain the same, the conclusion would be the same thing. So you're really going to get the same thing. No difference there if we had decided to run that as an upper-tailed test. Just watch the order that you subtract things in. All right, last part to this one. We ran the hypothesis test. Let's back up our hypothesis test results with a confidence interval for the difference. So we're concluding that the new book's harder, that on average those scores are lower in the new book than the old. Let's figure out by how much lower are they compared to the old book. So support our hypothesis test with a 99% two-sample t interval for the true difference in the means. And we will again interpret. Okay, to stick with the same ordering here, I'm going to use the new book as our first sample, the old book as our second sample, and our confidence interval, we're going to look at the average for the new book minus the average for the old book. Again, there's nothing wrong with if you want to do that the other way around, but I want my results to agree with my hypothesis test. Okay, so for our confidence interval, we start by looking at our best guess. Our best guess is the difference of those sample means. Plus and minus the margin of error. The margin of error is going to have first a critical t-score, followed by the standard error, which involves those standard deviations, squared, divided by their respective sample sizes. So this relates to the new book. For the old book, the standard deviation was 17.868, that gets squared. And in the old book, our sample size was 458. This t-score that goes here, again, you can get the value from StatCrunch. Somewhere back up in Part A, you're given the degrees of freedom for the problem, and this is a 99% confidence interval. So make sure you can get this, but the critical t-score here ought to be 2.581. All right, if we look at the difference in homework scores between the new and the old book, the difference here is negative 3.308. And that margin of error is 2.627. So, on average, it looks like the new book's test scores are about 3.3 points less than the old book there. Let's do our confidence interval value here. And we end up with an interval that goes from negative 5.935 to negative 0.681. The only thing that would change if we had done this the other way around is really this difference here would be a positive difference. You would end up actually with these same values. They would just both be positive, and obviously the smaller number would come first, followed by the larger number. And sometimes it is easier, especially when we do the next part, we're going to interpret the interval, to think about that difference as positive. But we can do this. Okay, so make sure you've jotted down what the answer is here. I think I have a clean slide that I'm going to use to go ahead and interpret that interval. Yep. And again, just keep in mind this was new minus old. Look at that interval. 0 is not in that interval, right? 0 is over here. This whole entire interval is negative. Since the whole entire interval is negative, think about when you get a negative difference. You get a negative difference when this first number is smaller than this number here. So we are, forget how confident, we are 99% confident that the new book's online homework, that on average those scores are going to be somewhere between 5.9 and 0.68 points harder, that their scores are going to be lower, and the difference, how much lower? Somewhere between 5.9 and 0.68 points lower on that new homework versus the old. So we are 99% confident that the new books homework scores so I'm going to change this to a positive, are between 0.681 and 5.935 points harder or points lower. Than the old book. So when you're interpreting that, just keep in mind the order that you subtracted them and what that tells you. These are all negative differences, so to get a negative difference, these scores had to be lower in the new book than they were in the old book. And by how much lower? Well, we're 99% confident that they were somewhere between 0.681 and 5.935 points lower on average than the old book. Again, this backs up the results from the hypothesis test. They should agree. If you get a different result based on your confidence interval, then you messed up one of them. Go back and make sure that those two results agree. All right, that wraps it up for this video. So it's been nice videoing with you. We'll see you in class. Thanks.